I want to talk about the theory behind ARPS. I think most of you know the ARPS equations. They're the exponential, hyperbolic, harmonic decline curves. Most people are familiar with them. If you're working at all as a petroleum engineer doing production forecasting or reserves, you're using these curves on a regular basis. I want to talk a little bit about the theory behind these things. Fairly straightforward, but I'm going to put a little bit of a twist on it and show some of the limitations that we need to be aware of. Okay? And when you're using these techniques, I sometimes see cases where they're used beyond the area where they should be used. And I want to make sure that we can get a good sense for where these things should be applied and some of the complementary tools that can be applied to make them more valuable. To start out with, we'll talk a little bit just about the theory behind the curves. J.J. ARPS developed these curves many, many years ago. And the concept is we've got some production data, and the production data just from observation has a decline associated with it. So we can draw a curve through that decline. There's no theoretical basis behind that decline curve. Okay, that needs to be made clear. It's empirical, which in other words means that it's derived experimentally through observation. But the thing that people maybe usually or sometimes don't realize is that there's an implicit assumption of constant operating conditions. And this can become very important. Okay? For example, picture a case where we have a well that is rate restricted. So we have rates that are held at a constant value. Clearly we can't do decline curve analysis on that. Okay? And the reason is the operating conditions aren't constant. We have a changing in operating conditions as we're dropping the pressure in a well like that. And there's lots of other cases like that. Picture a well that we put on compression. Well, the operating conditions have changed. Clearly, our decline curve that we've been using in the past is not going to suffice in the future. This is the exponential decline curve. There's a couple of things that we're primarily interested in here. In fact, two numbers that we're going to spend some time talking about. One is the initial rate, and one is the decline rate. When ARPS first drew this picture on a plot, he noticed that there was some curvature to the data. So one of the first things he noticed is that production tends to decline exponentially. And I think we've all seen exponential declines before. They start out very high and they drop and they sort of flatten out as time goes on. In fact, many things in nature decline exponentially. It turns out that when we take this data and plot it on a logarithmic scale, we get a nice straight line. And engineers love straight lines. Okay? Anytime that we're in a position to draw and extrapolate a straight line, it's going to make us happy. One of the reasons is you can't go too wrong extrapolating a straight line. You can go very vastly wrong extrapolating a curve. So extrapolating straight lines is okay. So one of the things that ARPS came up with is this equation describing the decline curve. And the two numbers we're interested in, the initial rate, that's just the production rate where the forecast starts. By convention, what we're normally going to do is apply that rate to the end of the data. Because really what we're interested in is where the production forecast goes. Okay? It is possible, if you want to do a history match, you can make that initial rate at the start of the data. But we're really going to be interested in the production at the end of the data or the start of the forecast. The decline rate is defined as the slope of that curve divided by the rate. Now we call this one the instantaneous decline rate. Okay? And you can think of it as drawing a line that's tangent through that data. When we talk about practical decline analysis, a lot of the time we're not going to really use that number. In fact, what we're going to be more interested in is a 2-point decline. And I'm going to draw these things on the board so you can see what we mean here. If this is production rate and this is time, the instantaneous decline rate is really taking 1 point and drawing a tangent through that point. Okay? That's instantaneous. The one that most people report when they talk about decline rates is what we call a 2-point or a secant type decline. And now we've got production data that looks like this, and I'm going to take 2 points on it, and I'm going to draw a slope through that line. Okay, so this is a secant decline. This is an instantaneous decline. really, these they mean the same thing, but they're slightly different numbers. Okay? From a practical perspective, we're more interested in this one. If somebody says, my well declines at 10% per year or 20% per year, they're talking about this sort of decline. Another word that we use for this is effective decline. Okay? So we're going to call that one effective decline. This one is an instantaneous or true decline. This is the one that's used inside all the equations, but it's usually not the one that we report. Okay? If you think about it, if you're an engineer that's reporting production and reporting declines, it's much easier to do it this way, because what you're going to do is take two production rates off your plot and simply determine the decline rate based on that. And then the normal convention for doing something like this is we would take the production rate here, and then we take the production rate after 1 year. Okay? And if we know the two rates there, we would simply take rate, this would be rate 1 minus rate 2, and we divide by the delta t. We divide by rate 1 and the delta t, which is 1 year. So that's just going to be 1. And then this is going to give us our 10% or whatever it happens to be. So calculating the effective decline rate is very straightforward. One of the things we'll notice in the software is that the, let's walk the right way here. The effective decline rate is reported here, and the instantaneous decline rate is reported there as well. If I change one of those things, usually the effective decline rate is going to be the one I'm interested in, and the other one will change as well. So these are linked together, they calculate each other, and I can input whichever one I want. Okay. So the decline rate, the initial rate, those are things that we're going to be interested in. If we look at these plots, we can determine the decline rate just by looking at the slope of that curve. This plot over here is a rate versus cumulative production plot. If we're interested in doing a production forecast, in other words, we want to know how the rate or the deliverability is going to vary through time, then we're probably going to want to do a rate versus time plot, which would be this semi-log plot here. But if we're interested in ultimate recovery or remaining recoverable reserves, then we're probably going to want to plot the data on a cumulative scale. So we plot the production data, rates versus cumulative production, and then we forecast that. And that turns out to be a straight line as well on an exponential graph, and it extrapolates down to the expected ultimate recoverable. So those two plots are probably the most important plots for production analysis in the last 50 years. And they're used almost every day. And they're very practical plots. Okay? So that's not something that's ever going to be replaced by the modern methods. It's something that is a good complementary tool to some of the other things we're going to be talking about. ARPS noticed something with the data that he looked at, and that was a lot of the data, when he started to look at it on a longer term basis, didn't remain exponential. In other words, when we look at it on a rate versus cum or a semi-log rate versus time, instead of having a very nice straight line, which would have been good, because engineers like straight lines, and forecasting that would have been easy. Well, it turns out that it wasn't going to be that easy. We started to see, or ARPS started to see, that the actual shape of this data would curve a little bit. So hence, the hyperbolic decline was invented. So we actually have two decline equations. We have the exponential equation, which we've talked about already, and we have the hyperbolic decline curve, or the hyperbolic equation. And the hyperbolic equation is, again, just another empirical equation, but it does a better job of matching the performance of most wells over the long term than the exponential does. Okay, so the hyperbolic is a more generalized and better fitting equation to most long-term production data, whereas the exponential will do a pretty good job either over the short term or just of approximating a data set. The hyperbolic is a more accurate match of the data over the long term. The hyperbolic decline curve introduces this B value, which you see on here. The B value really is a dimensionless number, and it can be any number greater than 0. ARPS set some guidelines for this. He said the B value should be anywhere between 0 and 1, for example. Okay, and we'll talk about the reasons for that a little bit later. But this B value really can be any number that you want it to be. Okay? And we call that number the hyperbolic exponent. That number will change the shape of that curve. And it turns out that what happens is if you make the b-value something close to 0, and we'll call that a mild hyperbolic equation, that looks something like this. And the production decline has a mild curvature to it. If you make the b-value something larger, such as 1, or even greater than 1, then what happens is the shape of that curve becomes more pronounced. And we have what's called a strong hyperbolic behavior. Okay, these shapes are shapes that are actually seen in different types of production that we see. For example, many of you have seen tight and unconventional gas or oil. When we have that situation, we tend to get strong hyperbolic behavior. And we'll talk about the reasons for that in a subsequent subject. Many wells exhibit mild hyperbolic behavior. So a lot of this, deciding how to apply these different decline curves is based on the observations of the data itself. What do you see in the data? Therefore, what am I going to apply in here?